Hi everyone, I'm Riccardo Nanni, a postdoc at UCSB in the Enigma group of Professor Enawi, and today I'm going to talk to you about my project regarding the probabilistic target selection of the highest redshift quasars. High-Z quasars are very important sources in the early universe, mostly because thanks to them we can study the formation and evolution of the first supermassive black holes and also their impact in the intergalactic medium in the epoch of ionization. Unfortunately, finding these kind of objects is not an easy task, mostly because the main method that has been used so far is based on color cuts. So people are constructing these kind of plots in which they know what are the properties of their targets, and so they use color cuts to select candidates that then they observe with spectroscopic follow-ups. But the problem is like going toward high redshift, these objects are becoming rarer and the number of contaminants is increasing, and so this method is quite inefficient, especially if you consider like using it for selecting observing quasars with future telescopes like Euclid or JWST. So what are we proposing here is like an alternative method based on the extremely convolution code made by Bowlby et al. 2009. That is actually a probabilistic classification model in which you're going to classify all the objects or all the candidates based on their properties. So for example, let's say you want to classify if an object is an icy quasar or a contaminant. So the probability of this object being an icy quasar is given by the probability of the object being a icy quasar based on its properties. In our case, we're talking about relative fluxes multiplied by a prior that in our case is just J band magnitude distribution. So the magnitude distribution in the detection band. And this is normalized by the total probabilities of this object being either coming from a quasar or let's say being a quasar or being a contaminant. So we used this method and applied it to a sample of objects coming from the Viking, decals, and Y surveys, and these are our requirements. And what you see here, this is a proxy of the colors in the sense that these are all relative fluxes, so flux is divided by the J-band flux, that is our detection band. And we wanted to classify all these sources in order to find out if there are high quasars in the Viking area. Since we expect the majority of these sources are contaminants, then we used also this kind of objects to train our extremely convolution model for the contaminant class. While regarding the quasar class, we instead use a high number of simulated quasars using the Magriers code from Magriers 2013, with using these parameters. And here you see what are the colors, let's say the colors of these objects in relative fluxes overlapped with our contaminants. And so what is actually the extremely convolution is doing is deconvolving the distribution and then is feeding them using a mixture of Gaussians in multidimensional Gaussians. And you can see like a display displayed here an example of a deconvolved sample coming from the contaminants data after using the XD code. And once you build a model for both the contaminants and the high quasars, in our case, we use like 3 different redshift bins, we classified our source and so computed the probabilities. And these are the probability distributions. So the red arrows here are actually known quasars in among our sources. And as you can see, our method is able to select these 2 targets, but it's somehow failing for these other objects. And the reason why is like, for example, this object here is a really faint quasar that doesn't look like the quasars that we simulated with Magrier's code. While for this particular redshift range, you can see that the probability distribution is mostly very low. And the reason is related to the fact that, as you can see, the quasars in this particular redshift range are overlapping really well with the contaminants. And that is degrading the probabilities that the XD code is actually computing when classifying these kind of objects. So at that point, the question is, are there any new quasars among the unknown sources that has been classified by our method? Well, what we need is future spectroscopic follow-up. In order to do so, we need to define a probability threshold based on maximizing our completeness and efficiency. And so we're going to observe then spectroscopically all the sources that are above this kind of probability threshold. But I can tell you that we were able to observe some candidates with the highest probability in our sample. And I'm going to show you now like these two examples, like these two new quasars in the Viking area that has been detected thanks and classified thanks to our method. So this is surely a success for the method that we are going to use. And since I have no more time to tell you more about that, I'm just going to leave you with my conclusion and future developments. And that's all for me. And I thank you for the attention.